right, good morning. Hello, hello. Okay, all set. Morning class. For those of you who have not used Twitch before, in case you're here already, in order to comment, I do believe you have to sign in. I will see if I can change that, but if you are here, please let me know. Please say hi. You might have to sign in first. Creating an account should be relatively straightforward, but I know there's been some issues before. Okay, so we're going to go ahead and get started. Last time on Tuesday, we left off describing essentially the basics of disinfection, why we care, what kind of pathogens we care about, and how to deal with them. Or maybe how we know how many are a problem, really defining that difference between sterilization and disinfection. So today I want to talk specifically about the disinfection process and really get into the types of strategies we will use for disinfection. So you probably all are very familiar with chlorine already. We use chlorine in a few different ways, however, and the first and most common would be free chlorine. Free chlorine being typically measured as Cl2 or perhaps as OCl. So we can apply it in the form of Cl2 gas, so chlorine gas. We can apply it in terms of sodium hypochlorite, which is probably what you're going to find in a bleach bottle at home, or calcium hypochlorite, where you have 2 OCLs for every calcium. One or the two of these is probably going to be what you find in a household bleach bottle, and it's probably also going to have a bit of base added to it. So these free chlorine reactions will look something like, I'll take NaOCl, and that'll dissociate into Na plus and OCl minus. And remember, I think mentioned last time that HOCl will be in equilibrium with OCl minus and H plus. You rewrite that a little bit. So this, all right, awesome. Glad to hear that. Thank you. And by the way, is the sound okay? Is this loud enough? Let me know if there are any issues. Okay, so sodium hypochlorite here, we go into that. Thank you. Go into this reaction, then we have that equilibrium reaction between HOCl and OCl minus with H plus. Now, if we do chlorine gas, this might look a little different on the front end. So Cl2 gas, when we react it with water, if I get this correct, and I think this is a forward reaction, maybe there's some chance it can reverse as well. But what it should do is it should react so we get the HOCl. So we took an H and an O from the water, got a Cl from the chlorine, and then we get H plus, because there's one extra H there, and we get a Cl minus. So if we apply chlorine in the gas form, we are actually acidifying the solution a little bit. So something to keep in the back of the mind for chlorination applications. Depending on how you're adding it, you might be causing a little bit of extra acid. if you're relying on that reaction with water. So that's basically what our traditional or conventional chlorination does, is makes use of specifically the HOCl. That's the stronger oxidant. It's a more powerful disinfectant. That's what usually we base our systems to try to use that molecule. Now, there's another molecule that occurs quite often, particularly in the presence of nitrogen. Nitrogen as ammonia, nitrogen as even as nitrates or nitrites typically will get you there, but this type of chlorine is called chloramines or combined chlorine. And this is actually what we use intentionally for our residual chlorine dosing. So we want a chlorine residual in our pipes to keep the pipes clean, or at least preventing bacteria from repairing themselves after the disinfection. We want some sort of residual effect there. And so chloramines are what we add, and the way we get them is by reacting this free chlorine with some sort of ammonia. It could be NH3 directly. These could react with organic matter groups that have an amine group, and then you get some sort of chloramine with other stuff attached. Generally, we think of this as ClNH2, if I've got that right. We can also have Cl2 and H. You know, I might actually have that this might be not exactly correct. I'm trying to remember. There's a sequence of them that are also going in equilibrium reactions back and forth, and basically protonating or deprotonating and balancing with the chlorine, how many chlorines are there. A bit slower of the reactions here are a little bit slower, but they do reach equilibrium relatively fast. And they are also pH dependent. Okay, so anyhow, the chloramines are what we add to the system, and this is actually also what you typically smell in a swimming pool. If you might think, oh, this pool's been chlorinated way too strongly. Well, it turns out that the chlorine dose might just be normal, but somebody peed in the pool and there's a lot of ammonia, and therefore you're getting these chloramines which volatilize and smell and irritate your eyes a lot more than otherwise. Now, before you just avoid swimming pools altogether, because that's gross, it could also just simply be sweat, because the same urea, ammonia groups exist in sweat, so maybe it's just there were a lot of people sweating in the swimming pool. Also, maybe not the most pleasant of thoughts, so perhaps you could just assume that there was a lot of organic matter in the water that filled the swimming pool. So swim at your own interest there. If it smells highly like chlorine, maybe don't spend as much time in it, if that's for you. Okay, tangent aside, chlorine dioxide is another form. We get, this is ClO2. This goes through some reactions, but generally this is the form that we're kind of looking at using. And so there's a little bit of more chemistry there, of course, but we can apply it in that manner and use it as a pretty effective disinfectant. Not going to go too much in depth with that at this point. Ozone is another disinfectant we use sometimes, and we'll use this for more than just simply disinfection. We will often also use it for advanced oxidation. And I just realized my pen pointer has been feeling funny, like stretched, and that's because it's spanning both screens. So let me just take a quick moment to fix that. Pardon the interruption. There we go. Okay. All right, that should make me feel better and should help me have clearer handwriting for you, I believe. Okay, so ozone, you may know it as a natural oxidant. We don't like it in our troposphere where we breathe. We would rather in our upper atmosphere where it's going to block ultraviolet light by absorbing it. It turns out we can use ultraviolet light to split it. It absorbs it very well, as we know from the atmosphere. So we can make use of it. It's a natural oxidant by itself, or we can hit it with UV light and do some advanced oxidation. Ozone by itself can be applied. We may have even solved a problem already about ozone, but it's a pretty strong disinfectant. Typically, you have to generate this on site, so there's a bit of a safety hazard here. It takes very high voltage to do so in a traditional manner, and it's a highly oxidative gas, so there's some inherent dangers, so it just requires proper engineering and safety maintenance, all of that. Can certainly be effective and is used widely, but some considerations there. Really, all of the disinfectants we do expect to have some hazards. Chlorine is a highly oxidizing agent as well, so shipping it, storing it, all of that requires some safety considerations. Ultraviolet light is another method. This is not chemical, but necessarily, but I guess a photochemical method. And here we'll talk about it in a few minutes, but essentially we are irradiating the water with UV light to cause specific points in an organism's DNA to dimerize and prevent them then from replicating that DNA. And last, we have advanced oxidation, which is not necessarily for disinfection, but since it's so closely tied to it, I'd like to talk about it within the disinfection context. A lot of times we'll use ultraviolet light to photolyze or split apart hydrogen peroxide, ozone, or some of my research lately has been looking into using it for chlorine, with the fact that we can use different light sources. This depends on how well these chemicals absorb light. And so if we have different UV light sources, that may be an advantage, so that we can use some other type of oxidant. It doesn't have to be ultraviolet light, especially for peroxide. There's also Fenton chemistry. Fenton reactions are essentially iron, Fe, either 2+ or 3+, let's say X+, and H2O2, and that will also go through some catalytic conversions. The oxidation state of iron will transition back and forth and will essentially split that into these highly reactive OH radicals. And this is what the UV would do as well. So this OH radical is really an exceptionally strong oxidant, will react with just about anything, including other OH radicals or hydroxyl radicals, and so that's a good endpoint to use and to create for our advanced oxidation systems. Okay, so regarding free chlorine, I mentioned a minute ago, HOCl is the stronger chemical than OCl-, so we often will aim to operate at a pH of 5 to 6 range. And in terms of our equilibrium chemistry, this is going to look like this. HOCl is going back and forth with H+ and OCl-. And this is going to have an equilibrium constant. You could write it KEQ. Let's do uppercase K. So our equilibrium constant there, this happens to be about 10 to the negative 7.54 under kind of standard conditions. It'll change a little bit with temperature. And as a reminder, the way our equilibrium reactions work is we can say that our equilibrium constant is equal to the products over the reactants and I'm writing with brackets here. Technically, it might be slightly more correct to do the squiggly brackets, indicating the activity of the molecules. For now, we'll assume that it's an ideal solution and all that, so we don't have to worry about that. And so if we had a reaction, so let me write it this way. If we had A molecules of A and B molecules of B in reaction with C and D here, then this general equation for an equilibrium constant becomes the concentration, molar concentration of A raised to the A power. And don't forget the brackets here. This means X moles per liter, or excuse me, this is the moles per liter of X. The brackets are indicating the units here, and it is always that way, so just make sure you don't forget that. Anytime you see the brackets, we must be talking about moles per liter. So back to here, the products over the reactants, and I already messed that up. This should be C. C is one of the products. C to the C power, the lowercase c. So there are C molecules of C moles of C is what this is referring to. Times, and this is important, this is multiplication, not addition, times the concentration of D raised to the D power, and A to the A times D to the D. B, excuse me. Okay, so that's the general form of equilibrium reaction. So in the case of our HOCl system, we could say 10 to the negative 7.54 equals our H plus to the 1 power, because we have 1 here, 1 here, and 1 here implied. I'm just going to erase those for simplicity, but I just wanted to show you, remind you, times Cl minus to the 1 power divided by HOCl. Okay, so that's going to be an equation that we will use very often to solve for, and of course HOCl is raised to the 1 power. So again, these raised to the 1 power, we can just basically ignore it because anything to the 1 power is just that itself. So this is hopefully just a quick reminder of equilibrium chemistry. I'm guessing you guys have seen it before. If not, and if you need a little bit more time on it, please let me know. We will be doing some problems with the equilibrium chemistry and all that. So you will have chances to review. And actually, we'll go ahead and dive right into it. With this problem, we have if 15 milligrams per liter of HOCl is added to a potable water supply for disinfection, and the final measured pH is 7.0, what percent of the HOCl is not dissociated? And we're assuming the temperature here is 25 degrees, and that is so that you could take a lookup table and say that KEQ for chlorine is 10 to the negative 7.54. Or you could maybe solve that chemically. Okay, so take a couple minutes, work on that. see if you can get that approach. I'm going to give you a couple minutes here, and then I'll come right back in a minute, and we'll kind of step you through it. So I'm just going to mute myself for a couple minutes. Okay, so hopefully you had a chance to take a look here. Okay, so we have some mass of chlorine being added to our system, and our question really is what portion of that is not dissociated? Now, this problem, as it's written, might trick you into thinking that you have to do the molar conversion from mass to moles and get that percentage that is not associated that way. However, you actually have enough information just with the pH. It doesn't matter how much you add, the percent is going to be the same. So if you thought to yourself that you need to go from the mass concentration to moles to do the molar ratio, you're not on a bad track, you're going to have to do that quite often when you are solving this type of problem. But we can actually get the molar ratio from, instead of this process, we could do the equilibrium constant really is defining the molar ratio. So we can get there a little easier than doing the mass to moles. A lot of times you will have to include both portions. So I'm not meaning to imply that you don't need this process, but this time we have a quicker process. So the KEQ again, we said that's going to be 10 to the negative 7.54. And that's going to be equal to our H plus divided by, or excuse me, times our OCl minus divided by our HOCl. With this, what we need is to know something about the H plus concentration, and fortunately our pH tells us that at pH, when pH is equal to 7, that means the H concentration is equal to 10 to the minus 7 moles per liter. That's because the P in the pH is really talking about, if we do P of X, really what that's saying is 10, let's say, let me write this different. Let's say P to the X equals Y. Well, what that means is log base 10 of, let's see, I'm blanking, not blanking, but I'm taking a moment here. So what that's going to mean is, so P then is, let me rewrite this. If we say P to the X equals Y, then what that's inferring is that the X is going to be equal to 10 to the minus Y. So P then is essentially negative log, let's say P of X is negative log of X, if I have that correct. Okay, my brain is just not quite on today, apparently, so I'm just going to leave it right there. We can expand that, and I'll probably touch on this next time when I'm thinking a little more clearly. But for now, we'll say that part is true, so that X is 10 to the negative Y. And that's just how our pH system works, and that's the P section works. And you can actually, by the way, say pKa or pK equivalent, and that would be 7.54. So that's the same, writing it differently, but it's the same effect. Okay. Anyhow, since we know that our H plus is 10 to the minus 7, then we can actually get a percent. What we're looking for is that percent of the HOCl not dissociated. So what that really is meaning is percent of HOCl in the system. Okay, so in order to get that, we do need that molar ratio. And in fact, maybe we can go ahead and write how we could find that percentage out. Would be saying that is HOCl divided by HOCl plus OCl minus times 100%. Okay, so that would give us our percentage that we're looking for. Okay, now we can manipulate this equation to find it. So let's go ahead and do that. So we can take this 10 to the negative 7.54 divided by the H plus, which was 10 to the negative 7, so fairly similar there, and say that's going to be equal to OCl minus divided by HOCl. Okay, so we're getting close, and we could go ahead and solve for that if we wanted to. I guess we'll go ahead and get that number written here just because. I'm going to do it in Excel just to be sure that I'm doing it right. So we have, let's just go ahead and write it out. Okay, that's our KEQ, and our H plus here is 10 to the negative 7. Both of these are in, well, this one's in moles per liter, and this one is probably also technically moles per liter, but it's just a little funny. Okay, so then we'll do the ratio here. OCl minus divided by HOCl. And that's just simply going to be that KEQ divided by that guy. Okay, so now we have a ratio, a ratio there that that tells us if we take one divided by the other, that's 0.28. That's telling us that there is less OCl minus than there is HOCl, which makes sense because it's slightly more acidic than the pKa. So since our acidity is 7, or our pH is 7, and this guy is 7.54, anything lower than that is going to make it so that we have more of the protonated version of our molecule. Okay, so 0.288 for that. So that's our value there. Now we need to convert this or manipulate it so that we can solve for the ratio up here that we're looking for. And to do that, one way to do it is to take this relationship and manipulate it into a form where we can use this. Now, here's a moment where if you wanted to, you could take the milligrams per liter here and solve for how many moles of each of these guys you're going to have, which you can do. Or you could, well, really probably the best way to do that would be to solve for the total, HOCl plus OCl minus. The total here, this 15 milligrams per liter is the total that was added. And it's going to be in one of the two forms. So the total here, so the 7.5 milligrams per liter goes to total chlorine. And that would be in the form of HOCl and OCl minus. And of course, since it's in milligrams per liter, we would need to convert that into moles per liter to get the ratio proper. Okay, so you could take that route, or we could manipulate this directly. Since we have this ratio already, we should be able to find the fraction. You know, if you knew that a third of, let's say, if you know this ratio, you know, 0.288 there are 0.288 OCl minuses per HOCl, then you should be able to find the percentage. It's just a matter of a little bit of algebra, right? So let's do this. Let's take this guy and say, let's divide the top and the bottom by HOCl. And I'm doing that because I see that that's going to get me a 1 on top, which is nice. So I'm just dividing, let's say, I'm taking it and I'm multiplying it by 1 over HOCl. I hope this is clear. So I just took this and I multiplied essentially by the same thing on the top and the bottom, so it cancels. It's just an algebraic manipulation. But what I end up with by dividing both the top and the bottom by HOCl, I end up with 1 over 1 plus OCl minus divided by HOCl. So this was a neat little trick that got us to the point where we can put this number in. This spot will go straight into here. And then we don't need any more math. There are certainly other ways you could have done this. This is just a bit of algebra that got us there kind of conveniently. You could solve all the way out, and effectively the math that you're doing is equivalent. This was just kind of a simple way through it. Okay, so let's take that Excel then and say our percentage that we're interested in is going to be equal to 1 divided by 1 plus this, and then multiply by 100. So we've got 77.6%. Okay, so the percent HOCl then, this is the stuff that has not been dissociated, or is the portion that is still in the not dissociated form, might be a better way to say that. That was 77.6%. Which is then our answer. Okay, did that make sense? Is there anything unclear there? Please let me know. Okay, so I'm happy to come back to that if there was a question and there's a bit of a delay here. So for chlorination, another thing we mentioned last time to consider is the disinfection byproducts. And really, this is a very, very wide range of products that can be harmful, that we want to look out for because we don't want harmful molecules in our drinking water or discharged into the environment for that matter. And so the way you might conceptualize this is classes of molecule types that are known to be problems. So trihalomethanes, and methane being a C with 4 hydrogens. In our organic chemistry labeling methods, this is implied that these are just hydrogens on here. But if you had a methane group, and by the way, this could be just for, just plain methane would be 4 hydrogens. If you had a methyl group, that means you have some other molecule over here. This R indicating it's just stuff. Who knows what it looks like, it's something, is the R. Now, the trihalomethanes then is when you have, instead of hydrogens, you've substituted them with halogens. So it could be Cl on 3 of the groups, or it could be maybe bromines. So you could have R, C, and then bromines. It's some sort of halogen, right? Maybe you have chlorines and bromines, something like that. Regardless, these things are more toxic, more carcinogenic and just more hazardous than when it was just hydrogens. Hydrogens being kind of the normal way of things. Another type would be haloacetic acids, where you have the same type of deal where you had an acetic acid group, and that was functionalized with all these halides, and then it becomes more toxic. So you can imagine that either you have these free floating in solution, or more likely, these are little subgroups of a larger organic molecule. And so then certain areas of these large organic molecules get functionalized in this way, and then that there's added toxicity to that organic matter that wasn't going to be a problem otherwise. So given that there are thousands of different molecules and conformations and all of that, the way we want to deal with these is really to mitigate the natural organic matter that's around to react with it in the first place. Another thing we can do is try to keep our chlorination at a sort of minimal level that's capable of achieving the disinfection that we need. So we don't want to over-chlorinate, because then we'll form more of these. Of course, we don't want to under-chlorinate, because then we won't achieve our disinfection. But it's just something that we have to keep in mind when operating these systems. Okay, now to determine the chlorine dose itself, what we need is a kinetics analysis, something that we've talked about a little bit already. And in particular, we want, or we need to use what's called the Chick-Watson kinetics. This is where we derive the concept called contact time. So the contact time is really describing the combination of the concentration of a disinfectant that a pathogen is experiencing multiplied by the time with which it's experiencing it. So you could have a low dose of chlorine, but exposed to that chlorine all day, your pathogen's going to die, right? There's going to be plenty of pathogens dying in that manner. It's slow, but it's going to work its effect over time. Or you could have a very short time, but a very high concentration of your disinfectant and achieve the same result, because in the kinetic analysis here, what we're going to see is they are closely related. That's because we've got a first order reaction. So the rate at which N changes, N being the pathogen concentration, is going to be equal to negative K times the concentration of chlorine, or of your disinfectant, times the number concentration of pathogens. So this is our dN/dt, and this is what we call the Chick-Watson kinetics. Now, what you'll notice here are typical kinetics that we've looked at before look something like dN/dt equals negative K times C. Or, well, rather, if it's an N here, then it's K times N, right? And then we can integrate that in a batch system or plug that into a CSTR system. However, here we have the new addition, I'll just change the color real quick, of the C to the N power. So the C to the N power, what that's referring to is the concentration of our disinfectant. That could be in milligrams per liter, that could be millimoles per liter, whatever makes sense for our system that we're dealing with. Now, the deal here is if we can assume that C to the N power is constant, which is sometimes reasonable to do, then the K and the C essentially are both constants, and we could even group them together and describe it as a K star is equal to K times C to the N power. So let me back up just a moment and explain what each of these terms are. So we know that the number concentration of pathogens, that's N, that's a number per liter. The C is a concentration of our disinfectant. I mentioned that could be kind of whatever the case is that we need. The N here, this N is what we call a dilution coefficient. We're going to assume this is 1 for ideal reactors, but of course if we had a non-ideal reactor, perhaps this is going to be less than 1. And even though we have a lot of chlorine, for example, it's not all mixing in properly, and some of the reactor does not end up receiving that concentration, if that makes sense. So that might be particularly important for something like an ozone contact system where we have ozone bubbling through the water, and perhaps if we don't design it right, then the concentration of ozone right where the bubbles are coming out is plenty high, but at the top of the water where the bubbles have gone through a lot of water and they have already dissolved, maybe the ozone towards the top of the water column is not getting into the water quite as much because there's less ozone available. So something like that could happen, and then our N factor would have to be reduced from 1. But for our class, we're pretty much going to deal with an N of 1. Okay, then the rate constant K here is what we call a coefficient of specific lethality. And this is specific per pathogen, and it's specific per disinfectant. So this is a specific pathogen or microbe to chemical or other disinfectant pairing. So if you are designing a system to do chlorine against poliovirus, and then you decide, okay, I'm going to use that same coefficient of specific lethality to model chlorine with norovirus, you're going to get the wrong answer because each virus, each pathogen, each bacteria are going to have slightly different reactivities with the disinfectant, different vulnerabilities. This is especially true if you're looking at Cryptosporidium, which has a very low coefficient of specific lethality with chlorine, for example. So that is specific to the type of pathogen and the type of disinfectant. And you'll see here this liters per milligram. That's actually showing you what kind of concentration of disinfectant we are using. So the units here, the units for K appear to be second order because they look like that inverse concentration times inverse time. However, if we assume that our concentration C is constant, then we end up having a first order system, and we can actually simplify and say that, well, let's use K star to mean K times C to the N power, and that's going to be in per time units, for example, per minutes. And so then we are back to our typical case of dN dt equals negative K times N to the 1 power. First order reaction, rate constant with first order units. So all of that should come back to what we knew and what we've worked with in the first place, but there's just a little bit of added complexity here in dealing with the concentration in addition to the rate constant. So the things to keep separate here for disinfection problems then are making sure you understand this relationship, this assumption that if the chlorine concentration is kept constant, then that's the way it works, and keeping the units straight in your mind. Okay, otherwise it's pretty much the same as we have already learned and done. Okay, so that's Chick-Watson kinetics, and you can see it applied in some of my past research here, just a graph showing that different amounts of, in this case we were producing singlet oxygen, which just highly reactive. It's almost a radical. And the higher concentrations we achieved, the faster we were destroying viruses. And this is a log plot for MS2, which is a bacteriophage. And we were destroying them. This was a photoactivated method, which was kind of neat. But essentially what we were doing was looking at these rate constants and trying to understand our system, about how much single oxygen we were producing and how effective it was in that system. Okay, so another quick little practice problem here. This is some poliovirus data from HOCl disinfection using 1.8 milligrams per liter. Temperature is 20 degrees C, the pH was 6.0. And so the problem's asking us to determine the rate constant of inactivation, assuming the Chick-Watson model applies with an n value of 1. Okay, so with this problem, what I want you to do is determine the K, that coefficient of specific lethality, and determine it in liters per milligram per second for of HOCl specifically. So you're going to need to use Excel or a graphing calculator to get to process this data. I will work through that with you here in a moment. So, but for now, I'll give you a moment to try that on your own. So I'll be back with you in a couple minutes. Feel free to ask questions. I will be at my desk, and I'll just mute myself. Okay, so I went ahead and got started here. I'm going to give you kind of part of the solution, show you what I did so far, and then kind of give you some directions on how to make use of the equilibrium equations that we have to solve this answer thoroughly. There's also an assumption here that we could make and get a simple quick answer, and then what I'll have you do is go ahead and do the full calculation using the equilibrium equation to make sure that we get a precise answer. Okay, so the question is asking for this K value that will be in liters per milligram per seconds, given that we're in per seconds here, of HOCl. Now we have a number here of the plaque forming units for poliovirus. Now this is not per liter, but it doesn't really matter. We could just either assume this test was in 1 liter, would be a fine assumption to make. There's not, or we could just ignore it altogether, because really what we're looking at is the rate of change of those numbers. So what we have here is the time and the number. What we ought to look for, because if we plot this, we expect it to be exponential, right? Exponential decay, something like that. But what we want is a way to linearize it to get a plot that's going to give us kind of a linear line that we can get our rate constant from. That's what we are looking for. So given that, we know that a first order reaction is going to do quite nicely if we look at the natural log of the number divided by the initial number. And if we plot that versus time, that should give us that nice linear line. So that's what I did in Excel. We have, so for this example, I went ahead and wrote in the time. I wrote in the values given to us there. And then I took the natural log of the current divided by initial number. I did that with this formula and just said it's equal to the natural log of this divided by this. And then I filled that down by, but also holding that denominator constant at the initial value. So the second value then is the 2 seconds divided by the 0 seconds values. Okay, so then I plotted that onto this, plotted the result of that, the natural log of numbers versus time, and got this linear plot, and took a regression of that. So I added the trend line, got that linear regression, and I told it to go ahead and fit to intercept at 0, which it was approximately there anyway, but since we want just y equals mx with this linearization, that's kind of a nice thing to do, and our r² value supports that just fine. So we have then y equals mx here, and that's equal, so y is equal to negative 0.3758x. So that m there, that slope, that's going to be our k star. So remembering back to our Chick-Watson kinetics a moment ago, we said that k star is going to be equal to the k that we're looking for times the concentration to the n power. And we're going to assume that n is 1. I said that here. So we're just going to get rid of that. So what we're solving for is this k. And now with Excel, we derived the k star. We know that the k star, according to Excel, was 0.758. Excuse me, 0.3758 per seconds. And so now we need k, and we can see that that's going to be pretty easy to solve for that if we know the concentration. So this is going to be 0.3758 per second divided by our concentration. So in this case, the concentration here, this is of course the concentration of HOCl. So we're looking for HOCl, not the total HOCl plus OCl minus, just the HOCl. So here we have, again, so remember HOCl is in equilibrium with OCl minus and H plus. So given that, we have to make sure that our calculations are aiming at just the amount of milligrams per liter of HOCl. Okay, here's where we could take a shortcut, and I'll show you the shortcut and then let you go ahead and do the solution without the shortcut as more practice with equilibrium reactions. So if we know something about the way our pH values look, let's say our concentrations of our chlorine species, so our chlorination equilibrium. So if this is pH 7, pH here, let's say 7, 5, and 3, and so on, that would mean this would be 9 and 11. Of course, this goes down to 0 and all that. But what I'm showing here is if we take a look at the fraction that is HOCl, it's going to look something like this. And the fraction that is, so this would be HOCl. And then the fraction that is OCl minus is going to look something like this. So you've probably seen these plots before, and this number right here, that corresponds to a pH of 7.54. That's our equilibrium constant. So just based on this alone, and knowing that the pH is 6, so at pH 6, we kind of expect that almost all of this is going to be in HOCl form. That will play out in the math when we see it, so that I would say probably over 95% of total, I don't know what's happening. My computer is bugging out a little bit. Please pardon that. I'm going to try to continue. I might restart PowerPoint, see if that helps. This is quite bizarre. I've got a new fancy computer a few weeks ago. It never happened on my computer that's 12 years old. So I'm going to restart PowerPoint real quick to see if it stops bugging out. Do you guys see the screen going black? I'm assuming so, because it looks like you do. So just a moment. Oh, did that fix it? No. Okay. Okay. Hopefully we're okay. So, as I was saying, over 95% of the total chlorine should be in the HOCl form at pH 6. So one thing we could do is solve this for if we assume C is 1.8 milligrams per liter, then we can get a K equal to, and here we'll use Excel. Then we could say, so if all of it went to HOCl, which is not exactly right, but it should be nearly, then we would say this is going to be equal to our, so K is going to be equal to K star divided by 1.8 milligrams per liter. And this is going to give us a value of 0.209 liters per milligram per second. I'll go ahead and do brackets there. Okay, so this is the case if all of it went to HOCl. So what I'm going to ask you to do now for the remaining time is try to solve this if it's not 100% and we have to go and do that calculation to see how much really is in HOCl form, because it's going to be, the number should be slightly, the concentration rather of HOCl should be slightly less than 1.8. So actually what I'm going to do, so this is the case for the assumption. And I'm going to add a little space in here to do the calculations accordingly. Okay, so go ahead and give that a shot. I will do it in Excel and then wrap up and explain in just a few minutes. Okay, so hopefully you had a chance to work through that on your own, or at least make an effort towards it to see how far you got. And actually, what I ought to do before showing you the solution, let me just go ahead and write this here. That assumption was K is going to be 0. Did I solve it? Yeah, okay, 208, right, 209 liters per milligram per second. Okay, so that was based on the Excel calculation we looked at a minute ago. Now, if we do this properly, we need to actually incorporate the stuff that we did in the other example problem to solve for exactly how much HOCl we have. And if you did that in Excel, that's maybe pretty handy because you'll have it all right there with you, which is what I did. So in order to solve this properly or precisely, we need to get the total moles of chlorine, so I'll just say total Cl. And really, I'm talking about the free chlorine here, but the total moles, this is going to be that 1.8 milligrams per liter of HOCl. That's how we added it. We added it in the form of HOCl, and with that, we can know that essentially it's then dissociating into HOCl and OCl minus. So with that, we can multiply this by the molecular weight, or excuse me, divide it by the molecular weight of HOCl. That's going to get us into mole terms. So we need the molecular weight of HOCl. Chlorine is 35.45, oxygen is 16, and hydrogen is 1. That becomes 52.45, all things told, grams per mole. So we can do that division. That's going to get us to moles of total, so the total moles of Cl per liter, so the molarity of it. And I'm going to go ahead and bring Excel over to show that part. So we have the moles total. I took that grams per mole, and I took 1.8, divided that by 1,000 because it was in milligrams, so we need it in grams. So 1.8 divided by 1,000, divided by the molecular weight. That gives us 3.43 times 10 to the minus fifth moles of chlorine per liter total. Now, from there, we need to say, okay, well, that's the total number of moles of chlorine, which is going to be either HOCl or OCl minus. So we need to go from the total into just the HOCl. In order to do that, we need to know, well, what percent of the total is this non-dissociated form? We did exactly that problem earlier, so all I did was I went up to our previous problem and just changed a number. Instead of using the H plus at 10 to the minus 7 for pH 7, I did 10 to the minus 6 for pH 6. So once I did that, it was pretty straightforward. I then I just told this, okay, that was going to be the same calculation from earlier. And then I said, okay, well, let me just multiply this percentage by the total and solve for, okay, exactly how many moles of HOCl are in the water in this case. So here, really, I just multiplied those two and divided by 100 because we were working with percent, and really I needed the fraction. So converted that back to fraction, multiplied the two together. That gives me the moles per liter of HOCl, which is exactly what we need to finish solving the problem. From there, we convert to, let me go ahead and write that out. So this was 3.34 times 10 to the minus fifth moles per liter. Excuse me, sorry, the total, let me go ahead and write this out properly. The total was 3.43. Times 10 to the minus fifth. The moles per liter of HOCl then, that was 3.34, 97% of that, times 10 to the minus fifth moles per liter. Okay, from there, we need to convert back to milligrams per liter, and so we take this and multiply it by our 52.45 grams per mole, and then multiply it also by 1,000 milligrams per 1 gram. And that's going to give us our final, almost final answer, our final amount of HOCl that we're going to use for our final answer calculation. So instead of 1.8, we actually have 1.75, essentially. So we have 1.75 milligrams per liter of HOCl. So not a huge difference, but as you can see, we're off. We would be off by a factor of 0.97. So we'd be slightly off. So our final calculation here then for K is going to be 0.21 instead of 0.2. Oh, okay. So let's say 0.215 instead of 0.209. So K then is equal to 0.215 liters per milligram per second. So this is when we did it the elaborate way versus when we did it the make an assumption way. So it is a difference, not a huge difference. That's all we've got time for. So have a good day. Enjoy whatever kind of fall break you can. And thanks for joining me. So we'll see you guys on Tuesday.